Welcome back.
Yeah, still the wrong video though. Okay. Well, I apologize for that. But for now, we're approaching the end of the class anyway. You're going to have to live with this horrible picture. Maybe I'll try it again later. Okay, because we're at the punchline anyway. All right, so you give me this random permutation of 1 through n. You then go searching for x plus a half, for instance, 4 plus a half. And that's for any x, could be anything from 0 up to n. So you search for anything that's not there. So that's really all the possible things you can search for. Something that's smaller than everything, that's 0.5. Something that's bigger than everything, that's n.5, and then everything in between. Well, we know what that is. That's equal to the expected number of min records in the, let's say, subpermutation that is less than or equal to x, plus the number of, sorry, that's the number of min records. You take all the things that are bigger than or equal to x, you count the number of min records. You take all the things that are less than or equal to x, and you count the number of max records. And that gives you all the things on the search path, right? These max records here, 2, 3, and 4, and the min records here were 5. Those are exactly the things you will encounter when searching for 4.5. And well, we know what this is, right? How big is this subpermutation? Well, this is the numbers this here is the numbers 1 through x. This here is the numbers x plus 1 through n. So, well, let's apply linearity of expectation. So it's the expected value of this plus the expected value of this. And we know what this is. This is h of n minus x. This is h of x. So if you go searching for 0.5 in this tree, then what you see are exactly the min records. Those will be 5, 2, and 1, right? That's if you go searching for 0.5. If you go searching for 9.5, you'll see exactly the max records, which are 5 and 9. And if you go searching for something in between, well, then you have to split the thing into 2, and you get some number of min records of the bigger stuff, some number of max records of the smaller stuff. So actually, if you think about it a little bit, then you'll realize that the worst thing to go searching for is the number right in the middle, n over 2 plus a half. But in any case, both of these things are smaller than hn. So this is smaller than 2. So h of n minus x is smaller than hn. H of x is smaller than hn, which means that this is less than or equal to 2 times the natural logarithm of n plus 2. Remember, we had this bound here. Yep. Yeah, so you search for 0.5, you take the subsequence of numbers which are larger, that's all of them, and the subsequence of numbers which are smaller, that's none of them. So you get a this here. So this was Hn, and this is H0, which by definition is an empty sum. So 0.
Let's say if like for both three, for example, if I have something on the left of me over that two, so I mean, is it guaranteed that it will always be records?
Yeah. Yeah, it's exactly what you will see is exactly the min records from the larger sequence and exactly the max records from the smaller subsequence. And the very special case, I mean, the two sort of extreme cases are when you search for 0.5, that's smaller than everything. And then you see exactly the min records we discussed, this one, this one, this one. And if you go searching for something that's bigger, then all you will see are the max records we discussed, 5, 6, and 9. Okay. So all that to say that the expected time to search for anything in one of these random binary search trees is at most 2 times the natural logarithm of n. So this is the analysis for when you go searching for something that's not in the tree. If you go searching for something that is in the tree, the only thing that happens is you find it sooner. I mean, maybe you go searching for 5 and you find it immediately. Much worse to search for 5.5. So certainly this gives an upper bound no matter what you're searching for, whether it's in the tree or not. Yeah. Oh, the half is just to say that I'm searching for something that's not in my tree. So I said the tree contains these integers, 1 through n. So if I search for an integer plus a half, it's just something that's not in the tree. Yeah, these are the things that are bigger than x plus a half. That's how many things are bigger than x plus a half. Right, so if I take n plus a half, then there is nothing bigger than that in the tree, 0 things. And if I take n minus 1 plus a half, so that's n minus a half, then there's 1 thing. So that it just works out perfectly. Okay, good. So let's remember that for the next time, that we have this random binary search tree that was somehow trivial to define.
Sorry, I have a question.
Yes.
Can you take a picture of the blackboard as it is, because it's very hard to see for me to see it and post it?
Of course.
Thank you.
My phone, of course, unlocks through facial recognition, which doesn't work because I'm wearing a mask. Fun times. Okay, good. So then the last thing that I want to tell you about today,
excuse me,
is, yes?
I have a question too. Like, what is the definition of min records and max records? Because here, when you see on that number line, you have drawn 5, 2, 3, 6, 4.
Mm-hmm.
Min records, we see it showing the lesser numbers, and there you defined it as the numbers greater than x.
So this is a picture of the min records of this whole sequence, this whole permutation. That's the 5, 2, and 1. The max records of this whole permutation are 5, 6, and 9.
Okay.
But when we're interested in searching, for example, for 4.5, we have to split into the subpermutation, which is smaller than or equal to 4, and the stuff which is bigger than or equal to 4. In the smaller one, we're looking for max records. So these things here, these are the max records from this sequence.
Okay.
In the larger one, these things are the min records of this sequence.
Fine, fine.
because you can always think of it, there's a lower bound on what you're searching for, and there's an upper bound. The lower bound keeps getting bigger, keeps getting closer, and the upper bound keeps getting.
So it's defined for the sequence.
Yeah.
Right, fine, okay.
Okay. All right, so once you believe this, that the expected length of a search path is only, is at most 2 log n, then, well, I think you can see that the time to build this thing is only going to be at most 2n log n. Why is that? Well, because at each point in time, you have a random binary search tree, and the way you insert the next element is you search for it. So what you pay is exactly the length of the search path for that thing. And it's even a little bit better because the thing doesn't even have n elements yet. It only has less than n elements. So, so certainly the time for each of those insertions, the expected time for each insertion is at most 2 log n. So in total, that's at most 2n log n, plus the 2 here. So 2n log n plus 2. That's great. And then finally, this random binary search tree, even if you haven't seen it before, you've probably seen it before because you have seen the quicksort algorithm. What does the quicksort algorithm do? The quicksort algorithm is a sorting algorithm that to sort a list of n numbers, it picks one of them uniformly at random and compares everything to that number. So for instance, it might pick 5 uniformly at random, compares everything to that number, splits the smaller stuff over on the left, recurses on it, splits the bigger stuff over on the right, and recurses on it. And so you realize actually the quicksort recursion tree is a random binary search tree. And the comparisons done by quicksort, they are exactly the same comparisons done if you use the appropriate random permutation. So the random permutation that starts with, or a random permutation that starts with 5, and then the smaller stuff is this way. All right, so there we got records, random binary search trees, and quicksort. And next class, we'll see how these can really be used in a data structure that does a lot of useful things that we'll end up using a lot in this course. But that is a good place to stop for today because we have all kinds of technical problems. Well, and we're right on time to quit. So thank you, Zoomers, for showing up, and thank you for all the people who came to class today.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you so much.
All right, bye.